I'm delighted to introduce our next speaker, Professor Anatolii Zhuchok from University of Potsdam and Lugansk Shevchenko National University, who will tell us about D groups. Please.
What a problem are we solving? I recall a definition of free algebra. Free algebra in the class K of universal algebras is an algebra F in K with a free generated system that is with a set of generators such that every mapping of set X into any algebra A from our variety, our class of algebras can be extended to a homomorphism from F into A. Algebra A of signature omega is a free in some class if and only if A is intrinsically free. So this algebra has generated set X such that every mapping from X into algebra A can be extended to endomorphism of algebra A. A non-empty class of algebras that is closed under subalgebras direct products and contains non-singleton algebras has free algebras. In particular, free algebras always exist in varieties and quasi-varieties of algebras. Variety is a class of algebras, I recall, that defined by some set of identities of the given type. And the study of varieties was initiated by Birkhoff. You can see on the screen example of the variety of commutative semigroups with identity xy is equal yx. And any variety contains free objects. One of the our main problem is to give a construction of free algebras in the class or variety of given algebras. In this work, we construct free algebras in the variety of diamonoids and abelian D groups, and also present the free generalized D group. So this is free object not in the variety, in the class of algebras, class of D groups. Okay, and next section, history of D groups. I start from definition of deassociativity law. Lode introduced deassociativity law. Non-empty set D with two binary associative operation is called diamonoid if this three conditions hold. You can see D1, D2, D3. So these axioms are called deassociativity law. And if operation coincides, then we have semigroup. We have only associative law. And if semigroup D with first operation or second operation is a monoid, so we have identity, then operation coincide. And this case is not interesting because we have semigroups. And how to appear these three axioms, D1, D2, D3? What is problem? So Lode for Lie algebras construct universal enveloping associative algebra. You can see this paper, and this object he called dialgebra. So universal enveloping algebra for Leibniz algebra is dialgebra. The definition, once again, associative dialgebra is a vector space of a field with two binary bilinear associative operation satisfying the associativity law. So this D1, D2, D3. So we have vector space of a field and plus these axioms. This is object. This object is a universal envelope in algebra for Leibniz algebra. And here connection, you can see proposition. Yes, if we have associative dialgebra and define bracket by this way, using two operations. Yes, usually we use one operation, here two operation of a diamonoid, then we get Leibniz algebra on associative dialgebra. So it means that this right Leibniz identity, you can see on the screen, hold. And we have Leibniz algebra. And example of diamonoids, example of the associativity law. Here we take set of all finite non-empty words and then define two operations using first letter and last letter of word. This. So in the first case, we use only first word, and the second operation we use first and second letter of the second word. And then we have algebra structure which satisfies the associativity law, this axiom. This is example of diamonoids. Okay, and next notion of de Groot's main object of talk. Lode proposed the problem of finding structures that generalize the concept of Lie group, and was algebra is corresponding Leibniz algebra. And such structure for Leibniz case has been called a different way. For example, Leibniz group, Lode group. And the first approximation to the solution of the indicated problem was given by Kenyon and Onge by constructing concept which generalize groups and called D groups. So this structure provides generalization of the third Lie theorem for Leibniz algebra. And here definition, we have several definitions of D group, and now we consider first. So diamonoid D is called a D group if there exists element E such that this condition hold. And second condition for any G element G, there exists inverse such that these expressions take place. And element E is called bar unit of the D group, and G minus 1 is inverse. So I want to note that bar unit exists in D group, but it is not assumed to be unique. So we can have a set of bar units, set of element E. And this set is called hollow path. The class of D group, according to this definition, is not a variety. And here example of such class of D group, take group and set M, which act on set on which H act on the left, and using this set, we can define two operations on direct product M times H by this way. Then we have example of our D group, and bar unit is E1, and inverse element for UH is EH minus 1. Okay. Second definition of the group. This definition use universal algebra apparatus. So we use unary-nullary operation. So we have a set with two binary operation, unary operation, and nullary operation. And this condition should hold. Element E is called bar unit, element 1 is called bar unit, and x minus 1 is said to be inverse of x. And this class of the group forms a variety. Because we use here unary operation, nullary operation, and we have variety, and so we have free object. Phillips proves that the system of axioms of the group not independent, and he found new independent system of axioms of the for the groups. And you can see here theorem non-empty set J equipped with two binary operation and unary operation, nullary operation is a group if and only if these four axioms satisfied. So here we have 5, here 4. So in this case, we have less axioms, and these axioms are independent. Okay, and let us consider the notion of generalized groups. A diamonoid is called a generalized groups if there exists a bar unit E, and for every x there exists two inverse elements. In the case of G group, we have only one inverse, unique inverse, but in the generalized case, we have left and right, and this left and right can be different, but also can coincide. And if these elements coincide, then we get usual D group. And of course, if binary operation coincide, then it becomes a group. So this is generalization, and for the group and also for group. Okay, and here example of such object. We have an abelian group and arbitrary subset of our group. And then we put direct product, introduce denotation x plus by this way, and using this denotation, define operation, this alpha and beta on the product, our subset of group by this way. Okay, and then we get generalized the group with a bar unit. This is bar unit, and left and right inverse element have such formulas for every x. So you can see that this is different element. Yes, in the case of the group, we have only one inverse, here two inverse and are different. Okay, and proposition, the class of all generalized group does not form a variety. And consider the variety of generalized group. Definition. Generalized group is a set equipped with two binary operation, with unary operation, two unary. Yes, right and left, and with nullary operation satisfies the following three axioms. You can see, okay, the base is diamonoid, and then this is bar unit, and this is left and right. So such D-groups are algebras of type 2, 2, 1, 1, 0. And if unary operation coincide, then we have usual D-groups. And as such, defined class of all generalized D-groups form a variety. And our plan in the future is to solve the problem of construction of the free project in this variety. Okay, and next section 3, how to construct free diamonoid or free object for algebras with de-associativity law. This is definition once again, recalling. So we have two semigroups and with de-associativity law, and first ladder in this paper construct free diamonoid, and then in our paper we construct diamonoid which is isomorphic to free diamonoid. This is our construction. We take three semigroups and natural number, direct product, then we consider pair such that length of first word more equal natural m, and define these two operations. In the second case, we use length of the word first word. And algebra fx is a free diamond. And next section. In this section, we construct the free generalized D-groups from this paper. And consider some properties of such structure. This is construction. We have free group and define free group with generated set X, and define operation on this product by this way. And then theorem Rodriguez, Salazar, Velasquez proved that f dx is free generalized D-groups. Okay. And I note that such structure can be obtained from the more general D-group first constructed in this paper. Okay, and here construction of monogenic case. Monogenic case, we take a set of integers, direct product, and these two operations. And then we get algebra FD1, and FD1 is free monogenic generalized D-groups with the hollow EFD1. This is hollow is the set of bar units, and with inverses which defined by these formulas respect to our fixed bar unit. And here corollary when our inverse left and right, this is condition when left and right inverse coincide. Okay, and next we consider some congruence on D-groups. If rho is a congruence on a generalized D-group such that the operation coincide, it is a group, we say that rho is group congruence. And if mu is homomorphism, then delta mu is a kernel of mu. And here presentation of the least group congruence on the free monogenic generalized D-group. So this map is an epimorphism inducing the least group congruence on the group FD1. A generalized D-groups is called commutative if both semigroups are commutative. And we prove with Günther Pils that there do not exist commutative generalized D-groups with different operations. So only with the same two operations, then we have group. Okay, next, free abelian groups. In this section, we construct free object in the class and variety of abelian group and consider sum the least congruence. Commutativity and abelianity in the groups have different meanings. I told that generalized the group is commutative if both operation commutative, but what is abelian? The group is abelian if we have this quality x times y by first operation equal y x by second operation. And in any abelian group, semigroups are anti-isomorphic. The fact that a class of algebras like generalized groups defined above is not a variety does not prevent the presence of free objects in it. Now we show how to construct free abelian groups of arbitrary rank. Here our construction, we have a free abelian group generated by X with unit E, and on the product X times Fix define two operations. And FRDX is free abelian group on the set X times EX times E is generated set for our algebra, and here you can see definition. I recall definition of generated set of the group, but it's important respect to fixed bar unit, because we can choose bar unit. We have set of bar unit, not only unique. Next, if rho is congruent on a generalized group such that factor is abelian group, then we say that we have abelian group congruence. And this proposition presents the least abelian group congruence on free generalized groups. So you can see a map. This map is epimorphism inducing the least abelian group congruence on our algebra F dx. I recall definition, rho is congruence on generalized group such that operation coincide, and we have group that we say that rho is group congruence. And now we present the least group congruence on the free abelian group. Not free generalized group, but on free abelian group. This is our joint result, and the map FADX to FAX defined by this way. We only multiply all elements in FAX, and then we have epimorphism which gives the least group congruence on free abelian group. And now we construct free algebra in the variety of abelian group. So now I want to note that this is a result free abelian group on set was given not for variety. This is free object in class, but here we now we construct free algebra in the variety. So we will use nullary operation, binary operation. Here construction define two binary operation, nullary operation, unary by this way. So the binary operation are defined in the same way as before, yes? But we add unary operation by this way. And also we take unary, we take nullary operation z minus 1. And then algebra with such signature is denoted by f(a)dx. And f(a)dx generated by x times e. Here definition of generated set. And theorem f(a)dx is free object in the variety of abelian deGrosse. Yes. And here reference, okay, first paper here. Phillips proved independence of axioms of deGrosse. This is our recent paper with Yuri and Günther, and in paper 17, the authors first constructed free generalized deGrosse. Also, paper 11 about such object, 19. And also Kenyon, we remember Kenyon consider the class of deGrosse in connection with algebra. Thank you for your attention.